자, 서울 디지털 포럼 2013 어느덧 이제 마지막 세션을 남겨두고 있습니다. 마지막 세션은 사회와 협업의 DNA입니다. 인류의 모든 선택은 생존과 진화라는 방향으로 나아가고 있다고 하죠. 지금 이 시점에서 경쟁이 아닌 협력이라는 곳에서 미래 비전을 찾는 것도 어떻게 보면 생존을 위한 노력이지 않나라는 생각을 해봅니다. 자, 서울 디지털 포럼 2013 어떤 분이 마지막 세션을 담당해 주실지 함께 해주시고요. 그리고 끝나자마자 바로 피날레 공연이 함께 있습니다. 그 시간까지 함께 즐겨주시기 바랍니다. 마지막 분을 경북대 최정규 교수님께서 소개해 주시겠습니다. 박수 부탁드립니다.
안녕하십니까. 저는 경북대학교 경제학과의 최정규 교수입니다. 제가 이 자리에 서 있는 것은요, 오늘 마지막 연사인 마틴 노박 교수를 여러분들께 소개해드리고자 입니다. 저는 이타성의 진화라는 주제로 연구를 하고 있는 사람인데요. 경제학자가 이타성의 진화를 공부하다 보니까 생물학 같은 주변의 학문들에서 어떤 이론적인 성과가 있는지를 끊임없이 살펴보고 또 그것으로부터 많은 배움을 얻어야 했습니다. 연구를 진행하다 보면 문헌을 통해서 항상 마주치는 학자들이 있습니다. 마틴 노박 교수님이 바로 그런 분들 중에서 한 분입니다. 마틴 노박 교수님은요, 수학자이면서 생물학자이십니다. 그의 공헌은 많은 분야에 걸쳐 있는데 특히 가장 눈에 띄는 것은 오늘의 주제와도 맞닿아 있는 협력의 진화에 관한 것입니다. 노박 교수님은 협력이 진화할 수 있는 가능한 메커니즘을 찾아내고 그 조건을 수리적으로 분석해내는데 탁월한 업적을 세우고 계십니다. 수백 편의 논문을 쓰셨고요. 그중에서 40편은 네이처지에 그리고 15편은 사이언스지에 게재될 정도로 학문적인 업적이 대단하신 분입니다. 최근 협력의 진화에 대한 그 자신의 연구를 가장 쉽게 풀어서 SuperCooperators 책을 내기도 하셨는데요. 한국에도 초협력자라는 이름으로 번역되어 있습니다. 그런데 사실 본인이 수백 편의 논문을 썼다는 것보다도 영미권에서 20년 이상 살았는데 아직도 오스트리안 악센트를 갖고 있다는 것을 더 자랑스러워하시고요. 특히나 본인의 억양이 터미네이터에 나오는 아놀드 슈발제네거와 비슷하다는 거에 굉장히 자부심을 갖고 계십니다. 오늘 마틴 노박 교수님은 우리에게 협력을 가능하게 하는 5가지 메커니즘을 소개해 주실 것입니다. 경쟁이 심해지고 그 경쟁이 주는 피로감이 피부로 느껴지는 시점입니다. 그러한 점에서 협력이 진화해온 그 여정을 마틴 노박 교수님과 함께 지켜보는 것 흥미로운 시간일 거라고 생각이 듭니다. 이제 노박 교수님을 소개해드리겠습니다. It is my great honor to introduce Professor Martin Nowak. 큰 박수로 맞이해 주십시오. 마틴 노박 교수님.
Thank you very much. Thank you very much. Thank you very much. I have to say, I have been to many conferences, I have given many talks, but this is more professional than anything that I have ever experienced. And when I came to the airport and I was picked up by 5 people, I thought, do they really mean me? Do they really have the right guy? When we came to the hotel, they looked through my suitcase and they checked if I had suitable clothes. When nothing suitable was found, they decided this must do. So this is not my normal talk, but a much better prepared talk. And in order not to get confused, I took some notes. 반갑습니다. So I'm not a chief executive. I have nothing to sell. I come only as myself, and I bring my ideas. And my ideas are completely for free. And I'm a scientist, and it is great that science has the last word in this impressive meeting. I believe that underneath this world of change, there's an unchanging reality. And as a scientist, I study this unchanging reality. and I study the mathematics of biology. And the title of my talk today is Evolution of Cooperation. And I will begin with a specific example on cooperation, just to start the story, and then we will go through the biology of cooperation. As the Fukushima nuclear plant was melting down, there were volunteer workers who entered this plant to get things under control. And one of these was in his 20s. And he knew that the choice might prevent him from ever marrying or having children for fear of burdening them with health consequences. And nevertheless, he did it. In an interview, he said, "There are only some of us who can do this job. I'm single and young, and I feel it is my duty to help settle this problem." So we see this is an act of cooperation among people. People cooperate. They sacrifice themselves for others. They help others. And we have to ask ourselves, why is there cooperation? Why are people cooperative? So now we go back in time very long. We go back in time almost to the origin of life. We go back in time 3 billion years. 3 billion years, this is a kind of cooperation that already existed then. These are bacterial cells. They form filaments. Ever so often a cell dies and it gives its life to feed the others with nitrogen. So a cell dies in order to help the others reproduce. And this is an extreme form of cooperation that was present on Earth already 3 billion years ago. Here's another example that was invented 125 million years ago, social insects. Social insects discovered eusociality. This means they are workers that do not reproduce, but they help another individual to reproduce, the queen. So we have to ask ourselves, why is it that biology has designed animals that give up reproduction in order to help another individual reproduce? This was already a problem that was considered by Charles Darwin. And then we come into our time, and we have human cooperation. So cooperation is abundant in nature, and we have to ask, why is there cooperation? So let's now go back a bit and ask the question, what is cooperation? In a simple way, cooperation is the following interaction. There is a donor, and the donor pays a cost. And there is a recipient, and the recipient gets a benefit. So I pay a cost, and somebody else gets a benefit. And the question is, why should I do this? Now imagine an interaction between two people. I pay a cost and he gets a benefit, he pays a cost and I get a benefit. We have a two-stage game. We are in the world of game theory. Game theory is a field of mathematics invented by John von Neumann in Princeton. So this is a prisoner's dilemma. And this prisoner's dilemma is the game of cooperation that I have just introduced, but now two people can decide. You have to decide whether you want to cooperate or defect, and I will decide whether I want to cooperate or defect, and then we will see what we have to do. Benefit is greater than cost, is greater than zero. So now I ask you, who wants to cooperate with me? Please raise your hand. Please raise your hand if you want to cooperate. Who wants to defect with me? Please raise your hand. No defector in Korea. So this is how you analyze the game. You don't know what I will do. Let's assume I cooperate. If I cooperate, your payoff is better if you defect, because B is greater than B minus C. If I defect, your payoff is better when you also defect, because 0 is greater than minus C. Therefore, no matter what you assume I might be doing, no matter what I will do, it's better for you to defect. If I analyze the game in the same way, we end up with the Nash equilibrium. So the Nash equilibrium is mutual defection. And that's bad, because this is the desired outcome. The better outcome is if we had both cooperated. But the Nash equilibrium is defection. And this is the dilemma. In game theory, you call it rationality. Rationality is precisely the way to figure out what the Nash equilibrium is and then play the Nash equilibrium. So the dilemma is, do rational players, in this narrow-minded sense of rationality of game theory, do rational players defect and end up with a low payoff, 0? And in that game theoretic sense, do irrational players might cooperate and receive a higher payoff, B minus 0, B minus C. Many experiments as this one show that people are not rational. People want to cooperate. And I want to discuss with you why you want to cooperate. I will give you the explanation why many people in Korea are cooperative. Before I do this, I say one more thing, and this is you don't need the game theoretic Nash equilibrium rationality in order to actually understand that natural selection chooses defection. In any well-mixed population, defectors are better off than cooperators. Defectors increase in abundance driven by natural selection until everybody defects. And therefore, natural selection needs help in order to establish cooperation. And what is the help? What is this that we can do that natural selection sees the advantage of cooperation? And there are many thousand scientific papers on this question, and I have proposed that all of these papers can be summarized in 5 mechanisms. And these 5 mechanisms are direct reciprocity, indirect reciprocity, spatial selection, group selection, and kin selection. And I will discuss with you these 5 mechanisms in turn. Direct reciprocity is the idea, I help you, you help me. So we have a repeated game. We play the game not once, but again and again. We come into the world of repeated games, the world of the repeated prisoner's dilemma. And Robert Axelrod, a political scientist, asked in the late 1970s, what is a good strategy to play this game? And he organized a computer tournament. And in this computer tournament, he received computer programs that played the game against each other. And the surprising thing was, the simplest of all programs that was submitted won. It was just a 3-line program. It was submitted by Canadian game theorist Anatole Rappaport, and was the following strategy, tit for tat. Tit for tat is, I start with cooperation. If you cooperate, I will cooperate. If you defect, I will defect in the next round. And this won the game. The results were analyzed. The tournament was repeated. New strategies were submitted. One person submitted tit for tat again, and it won again. It won twice. It was the world champion in the repeated prisoner's dilemma. But there was one weakness, one Achilles heel of the world champion. Tit for tat is unforgiving. If 2 tit for tat players play against each other and one makes a mistake, the other one will retaliate. This was the beginning of my PhD thesis about 20 years ago. We wanted to know, what do we do with that information? In Axelrod's tournament, there was no possibility of mistake. If you take into account mistake, tit for tat is not a good strategy. So what we said, let natural selection design a strategy. We start with a random ensemble, and what we first observed in a random ensemble, the first strategy that emerged is always defect. If people play randomly, the best thing to do is always defect. But fortunately for my PhD thesis and career, it wasn't over. What happened next was we observed tit for tat. Tit for tat invaded always defect and catalyzed the swing to cooperation. But it was not here to stay. It was quickly replaced by another strategy, generous tit for tat. That was a surprise. So what is generous tit for tat? I start with cooperation. If you cooperate, I will cooperate. If you defect, I will cooperate with a certain probability. This is the evolution of forgiveness. This is a recipe to save many relationships, many marriages in the US and in Korea. A random device to forgive. So we are now with generous tit for tat, but it is not the end of the story. What happens next was surprising. Random drift brought us to always cooperate. If everybody is nice here and I play unconditional cooperation, I'm a neutral variant. And neutral evolution will bring it to always cooperate. If we always cooperate, you can guess what happens next. You invite always defect. And you have oscillations. You have a little mathematical model of human history. Oscillations of war and peace. Economic cycles, prosperity and collapse. All my work on cooperation in the last 20 years has shown cooperation is never fully stable. There's always ups and downs. You have to build it, it will be destroyed, you have to rebuild it. This was the first mechanism. The others will go a bit faster. So now indirect reciprocity. Indirect reciprocity is the idea, I help you, and somebody will help me. Here's a Vincent van Gogh painting of the Good Samaritan. Whatever his motive was, it was not first round of a prisoner's dilemma, it's better to cooperate. Instead, the idea here is that we help people and people realize we are helpful, and that will mean that other people help us. So the idea is that indirect reciprocity works via reputation. A helps B and the reputation of A increases. A does not help B and the reputation of A goes down. This brings us to gossip. Gossip spreads reputation. Some people observe the interaction, others hear about it. People are obsessed with gossip. They talk to each other about others. They evaluate each other's actions. In the modern world, this gossip spreads on the internet. It's the evaluation of buyers and sellers on eBay. It's the evaluation of stores. These games of indirect reciprocity are cognitively demanding. They lead to the evolution of social intelligence. They lead to the evolution of human language. Arguably, the games of indirect reciprocity, that's what made us. My friend David Haig at Harvard said, for direct reciprocity, you need a face. For indirect reciprocity, you need a name. This is very interesting. In order to play a repeated game, I have to recognize you. In order to play indirect reciprocity, I have to be able to talk about you to others. Third mechanism, spatial selection. We are now in a world of distributions, of spatial organization, and the idea is neighbors help each other. Clusters of cooperators can prevail in such a setting. We can extend this to social networks. In social networks, you cooperate with your friends. Friends help each other. This spatial evolution has interesting mathematical properties, which we call spatial dilemmas of evolution. They give rise to interesting mathematical structures like a kaleidoscope, dynamic fractals, spatial chaos, and we have studied them for many years. This was the third mechanism. The next mechanism, group selection. All I say about group selection is a beautiful quote by Charles Darwin. There can be no doubt that a tribe, including many members who are always ready to give aid to each other and to sacrifice themselves for the common good, would be victorious over other tribes, and this would be natural selection. He imagines here the competition of two groups, and in one group people help each other, and that group is better than the competing group. Last mechanism, kin selection. You help genetic relatives. Here's a quote by G.B.S. Haldane. I will jump into the river to save 2 brothers or 8 cousins. G.B.S. Haldane was a founding father of population genetics. He was also politically very active. He was a dedicated communist, here addressing a group of British workers. I have presented 5 mechanisms. Direct reciprocity. The idea is I help you, you help me. Indirect reciprocity is the idea I help you, somebody will help me. Spatial selection means that neighbors or friends help each other. Group selection means that groups of cooperators outcompete other groups. And kin selection means that genetic relatives help each other. These are the 5 mechanisms. Each one of them can promote the evolution of cooperation. Let's step back and look at the bigger picture. What is Darwinian evolution? Traditionally, Darwinian evolution is based on 2 fundamental principles, mutation and selection. Mutation and selection are the classical ingredients of the Darwinian process. This means we have a competitive nature, we have conflict, we have fight, we only have selection and competition. For these 2 principles, my work, my proposal has added a 3rd fundamental principle, and this is cooperation. Our understanding of evolution is incomplete without cooperation. We have to realize how important cooperation is to explain the world that we see around us. Cooperation is needed for the origin of life, for the evolution of the first cell, for multicellular organisms, for animal societies, and for humans. Cooperation is needed for human success, for prosperity, and for well-being. I'm almost at the end of my talk. And I want you to look at this beautiful image here. This is the miracle on the Han River, the miracle of Korea, its economy, its prosperity. It has been established in record time. I think the secret of success of Korea is the cooperation among the Korean people. And I have a very positive message for you. The positive message is that in all my work over the last 20 years, I have observed the following. Winning strategies of cooperation are hopeful, generous, and forgiving. You don't win the game of cooperation unless you have these three properties. What does this mean, hopeful? Hopeful means if I meet a new person, I'm hopeful that I can establish cooperation. My first move is cooperation. Generous means in any one interaction with another person, I do not have to win. I'm happy sometimes to take slightly less than 50%, but I have many collaborative interactions. Finally, forgiving, if there is defection, if defection happens, if a mistake happens, or even intentional, I have a mechanism to forgive. I have a mechanism to go beyond it. I have a mechanism to re-establish cooperation. We have to forget bad things that happened in the past, and we have to look for the future. We have to look for the productivity in the future. Winning strategies are hopeful, generous, and forgiving. But there is a warning. And the warning is cooperation is never fully stable. There are always cycles. You will always have economic prosperity, economic collapse. You always have to work very hard to maintain what you have, and once it's destroyed, you have to work even harder to rebuild it very quickly. We are not talking about economic equilibrium. In my opinion, this does not exist. It is always oscillations, and you have to ask yourself, which mechanisms do you have in place to rebuild cooperation once it has gone? This is very important for a government to know how to deal with economic downturn and to react quickly. Now, in the last minute of my talk, even bigger picture. What we are seeing here is our spaceship. It's that which carries us through the universe. And we have a mandate. We have to look after it. We have to maintain it. We have to keep it. We cannot think about ourselves. We must learn global cooperation. In human history, we are used to interactions in small groups, competition in small groups. But in the modern world, this is not enough. We need more than that. We need to learn how to cooperate in a global situation. And I think the internet, the World Wide Web can actually help us, because this goes beyond the boundaries of countries and enables people to cooperate with others that are actually far away. But it's not enough. There's one more thing we have to learn. We must learn to cooperate with future generations. We have to pay a cost such that the people who come after us have a benefit. We actually have to leave a world for them that is comfortable and habitable. And this is the most complicated task that we have before us. And I have no mechanism for it yet. I don't know yet how to do that. We have to learn how to cooperate with the future. Because in the very large scale, cooperation is needed for the stability of intelligent life. Intelligent life, a great invention of evolution, it moves very fast. It moves globally. It can destroy. And that's a problem. That's a danger. Cooperation is needed for the stability of intelligent life. Here, the end credits of my talks. I thank all these people with whom I have worked over many, many years. And I have learned very much from them. Many of them have been my students, and now they are professors at prestigious universities. But I came to Korea 5 days ago, and I already have a long list of Korean collaborators. So these are the new cooperators in my team. And many of the ideas that I've presented here, they are in this book, SuperCooperators, which also came out in Korea. And it's also a great opportunity for me to promote the book of Professor Choi, who will now come back on stage. Thank you very much.
재밌게 들으셨습니까? 예, 제가 여기 왜 나왔냐면요. 여러분이 궁금해하실 만한 질문을 좀 던지려고요. 그래서 우리에게 주어진 시간이 한 10분 정도 남짓 있는데요. 제가 한번 여러분이 질문하실 만한 이런 얘기를 좀 같이 나눠보도록 하겠습니다. Thank you very much for your talk. I enjoyed that, and especially the one, the slide you showed us where my book popped up. So, 이게 저희가 협력하는 방식입니다. I said this is how we cooperate each other. It seemed like all of us were watching your journey to quest for the secret of the evolution of cooperation, right? Could you tell us how your journey started?
Yes, the question is, how did my journey begin? And the answer, it was a random event. You know, evolution likes to work with random events. I was a student, and the professor gave a lecture on prisoner's dilemma. I asked one question, and I became his student. And I did my PhD thesis with him, and I have worked with him ever since.
Okay. As you showed us at the end of your talk, you introduced your collaborator as cooperators, right? So many of us might be wondering how the work is being done in your lab. Could you tell us a little bit about that? I mean, especially I'm wondering if everybody in your lab is super cooperators.
Yes, I think everybody in my lab is a super cooperator. I have the following strategy. People who have come to Harvard have passed many, many examinations, many tests. So when they come to me, I want to provide to them complete freedom. I do not ask them to do anything at all for me. I'm just here to promote their creativity. I give them unlimited possibilities in order to express their creativity, and we work together. We are colleagues, friends from the very beginning, and they are friends with each other. Everybody helps each other. It's a very collaborative, completely non-competitive environment, and I think you can create it by realizing that creativity comes from freedom and from opportunity.
So there is no defector in your lab?
No, there are no defectors in there.
So now let me move into the main questions. So you just suggested 5 mechanisms that lead the evolution of human cooperation. Is there any particularly important one, do you think, when it comes to the people?
I think for people, the most important one is indirect reciprocity. Humans are the only species who have unlimited indirect reciprocity because we have language as a mechanism of unlimited information transfer. And other animals are restricted with indirect reciprocity to direct observation of what happened. And for humans, this is not the case. And I think indirect reciprocity interactions are really the one secret to the evolution of humans. They explain what humans are about because they give rise to social intelligence and human language. And social intelligence means we look at each other and we look at social networks and we ask the question, who does what to whom and why? And this is demanded by indirect reciprocity, and this made us humans.
So related to your answer, so do you believe humans are unique in the...
I think humans are unique in the sense that they are the only organism that uses all 5 mechanisms and indirect reciprocity to full extent.
How about institutions? So, for example, we had egalitarian institutions that had persisted for a long time among our ancestors. That could have played an important role in the human cooperation.
So
right?
it is a very interesting question to ask what is the selection pressure, the evolution of institutions. So people don't live in a society like cells, or so where everything is uniform, everything goes. Instead, they have made institutions which organize and which administrate and which govern. And on the large scale of evolution, we have to ask where these institutions come from and how these institutions function and to what extent they promote cooperation. I think successful institutions promote cooperation, successful government promotes cooperation.
Yeah. Somewhere in your book, you describe the game that all people on Earth are playing, the climate game, right? So you wrote, unless people fully realize the extent to which the planet is in danger, people will fail to do enough to save it. I believe that climate change will force us to enter a new chapter of cooperation, right? So I think this is a very important point. And when it comes to the climate game, it seems to me that it's more difficult to solve because not only current generation, but also future generation is involved as a player. Could you tell me a little bit more about the intergenerational?
Yes, so the problem with climate game, with preserving the climate, is how to cooperate with future generations. And I was impressed once when I met the science minister of the United Kingdom, and he told me there was a forest, and the forest was about to be destroyed. And there was one argument that prevented the destruction of the forest, and this was, you would not have this forest if it was not left to you from previous generations. Okay. Therefore, it is your duty to leave it to future generations. You cannot destroy it. This argument carried the day. This inspired me to do an experiment. And in this experiment, we have groups of people who can harvest a resource to exhaustion or leave it for groups of people who come after them. In a normal setting of the game with Harvard students, the resource is almost always destroyed. They leave nothing for the people who come after them. Then we make a variation of this where we say, you cannot just take out whatever you want, but you have to vote. You have to vote how much to take out. And so the democratic approach maintains the resource, and most resources are left for future groups.
That's a good news. Democratic, procedure can solve the problem, right? I think we are getting the end. What would be the implication that humans are cooperative, especially where competition is everything?
I think, so you should not think that there's just cooperation. There's always interplay between cooperation and competition. So there is a tension always between competition and cooperation, and this tension makes the interesting society, successful society. You have always both there. You have always natural selection leading to competition and cooperation. You want enough cooperation to be productive. You want also competition to be efficient. You need both. You always need both.
Yeah. You know what? We are proceeding very efficiently, so we have a little bit time, right? So 제가 아놀드 슈바젠의 그 발음을 한번 부탁을 드려볼까 합니다. Could you tell the I'll be back?
Thank you for inviting me to Korea. I'll be back.
So I think we have many students here and graduate students here. Could you give them a piece of advice as a senior scholar?
Yeah, my advice for the young scientists, for the young people, is to follow their dreams, to be enthusiastic. So you have to ask yourself, what is it that I'm good at? Go after this target. Do not have respect for the previous generation. They have worked very hard, they have achieved very much, but you have to think you can do better than this. I think this is the right attitude.
Did you prepare wrapping up remarks for us?
Yes, you have invited me to Korea, and I want to invite you to Harvard. 고맙습니다.
Thank you very much for your attention, and thank you very much for your talk and discussion. Okay, that's great.
Thank you very much.
Thank you. 감사합니다.